you all enjoy Madeline's presentation.
All right, well, thank you, Jorge, and thanks to everyone for attending today. I'm going to be presenting my master's work on the upstream propagation of sea level cycles in Fluvio-Deltaic environments, time lags, and the dynamics of the fluvial surface. If none of that makes sense, don't worry, I'm going to break it down as we go. So here's just a roadmap of where we're going in the presentation. I'll start with some background information on deltas and changing sea level. Then I'll go into some past work that's been done in this area, so you're aware of the history and the foundation of the work that I did. Then I'll detail the work I did and how I did it. And of course, I'll close with a summary to recap everything and explain why this work is important. So a delta, what is it? A delta is a low-lying landform created when a river enters a lower energy system and drops its sediment load, right? So a river moves pretty fast and carries all sorts of sand and silt and stuff as it goes. And when it encounters another water body, it slows down and drops all that sediment. And you can see these examples on the right. The Wax Lake Delta and the Atchafalaya River Delta, both in Louisiana, and part of the better known Mississippi River Delta system. Coastal areas, and deltas specifically, are home to over 500 million people worldwide. And because deltas are low-lying, the people in these areas are in particular danger from changing sea level and increased storm activity. So understanding deltas and how they evolve is an important step in protecting our vulnerable coastal communities. And again, on the right, you can see those two rivers in Louisiana depositing sediment in the Gulf of Mexico, and you can see the deltas form over time. These formed in relatively short timescales, over decades. But over geologic time, hundreds of thousands of years, that sediment lithifies or turns into rock. And if we take a slice through the delta, we could see an outcrop that looks like this, where the strata or layers of rock are a record of sea level changes. Sea level experiences changes or cycles every 100,000 years because of changes in Earth's orbit that alter the amount of global ice. These sea level cycles are captured in deltaic architecture, the rock record, and we can interpret that record to reconstruct past sea level. Reconstructing past sea level in this way is the job of sequence stratigraphers. Sequence stratigraphy is the branch of geology that seeks to understand and explain outcrops of sedimentary rock such as this. To simplify how outcrops like this formed, we can simplify this bird's eye view of a delta. So we're looking down in here and we see the river coming in and depositing all this sediment. This is a delta. And we can simplify this by kind of changing our perspective and looking at the delta from the side. And this is really what the cross-section is. We simplify this further and can use simple geometry to represent the delta. Here, we have the river coming in, represented by the sediment supply arrow, because it's carrying sediment. It's coming in and it travels across the fluvial surface. To the right, you've got our sea, right, our sea level, and where the fluvial surface and the sea touch is the shoreline. I refer to this part, kind of the upper portion of the fluvial surface, as the upstream, and this part as the downstream. And then this bit underwater, that's the foreset. So, early sequence stratigraphers assumed that the fluvial surface was flat. So during sea level fall, there would be regression, where the shoreline would move out. The river would then erode sediment off the top of the fluvial surface and deposit it at the foreset. During sea level rise, transgression would occur, where the shoreline would move landward and there's only room for deposition on the fluvial surface. This is early work. People expanded on this kind of original geometry to include a slope of the fluvial surface. So instead of being flat, we've got this slope here, which is a little bit more realistic. This slope means that as sea level is falling, right, you can see the regression arrow, sediment can actually be deposited across the whole fluvial surface when before there was erosion happening. All of these responses depicted here are uniform, the same thing happening across the fluvial surface at the same time. Recent work, kind of depicted in this box in the bottom, builds on that slope to account for changes in curvature of the fluvial surface, which is an even more realistic way to model a delta. When we allow for curvature, this changes the patterns of erosion and deposition that we saw before. Now, we see deposition in the upstream during sea level fall, and the foreset, and then erosion at the shoreline. During sea level rise, we see deposition in the upstream, at the shoreline, and then erosion in between. And this changes the shape of the fluvial surface. You can see here that we've got a concave shape, right? So this dotted or dashed line represents time equals 2. So our second time, you can see our shape is concave. And then here our shape is convex. And if we animate this curved sloped fluvial surface changing with sea level, we get this movie where you can see we would have sediment supply coming in this way, our sea level here, and this here would be the fluvial surface. If you watch the shoreline as sea level fall and compare it with the upstream, you can see that the shoreline decreases in elevation as sea level falls, and the upstream is still increasing. They're doing the opposite thing. Similarly, during sea level rise, the upstream decreases in elevation, but the downstream increases. This opposite response that's happening tells us that there's a time lag in the upstream response to sea level. A time lag means that there's a delay in when the upstream is feeling the effect of sea level from when sea level actually changed. So my work takes this understanding of how the fluvial surface evolves out of this modeled theoretical world and advances it by using experimental data because we want to better understand if there's a time lag visible outside of theory in an experiment and contribute more information on how sequence stratigraphers can interpret outcrops to reconstruct past sea level. So here's another outline, but one that's just a little bit more of a detailed guide of the work that I did. I'll start by explaining the flume experiment and what a flume experiment is. Then I'll explain my first analysis that looked at the change in elevation across the fluvial surface. Then I'll describe how I worked to understand the time lag that we observed and the changes in slope and curvature of the fluvial surface in the experiment. Then I'll walk through how changing patterns of erosion and deposition drive the changes in curvature. I'll explain what I learned from this experiment into another experiment and see if the changes are noticeable under other conditions. Then I'll tell you why this work is important, and I'll close with a summary. So first, I'm going to credit the Tulane Sediment Dynamics and Quantitative Stratigraphy Group for conducting the experiment and taking such great data. They use flume experiments to understand the natural world. Flume experiments are used to simulate what happens in the field in a controlled, scaled-down setting. What we see in flume experiments is a proxy for what happens in a field-sized delta, because deltas can be as big as 10,000 kilometers, and flumes let us observe those systems on a small scale. Here, the delta grew to 1.3 meters under constant sediment and water input and was well documented with a camera for a bird's eye images every 15 minutes, and they also scan for topographical information every hour. The delta grew under two types of sea level with a background sea level rise rate. The first was a low magnitude, long period sea level cycle, and period here is the amount of time it takes for sea level to go up and down one time. So in this case, the low magnitude long period in this blue means that sea level changed slowly and only by a little bit, about 5 millimeters up and down. The second type was a high magnitude short period where sea level changed rapidly and by a lot, about 12 millimeters up and down. When sea level doesn't change a lot, this low magnitude scenario, there are many more autogenic processes that occur. Autogenic processes are the internal changes that happen within a delta, such as changes in the river channel. And then here are two examples of autogenic factors from the experiment. In blue, you can see river flow that's kind of like a sheet covering the fluvial surface. In red, you can see a single channel. Throughout the experiment, the river changes between these two types of flow and moves around the fluvial surface. And these changes can obscure the signal of changing sea level because they leave a large impact on the deltaic record. So we limit the effects of that changing river flow by taking the radial average, which means we average the whole fluvial surface into one profile, just like this, which may look a little familiar. I showed it in the beginning. So once I simplified it to kind of look like this, I started analyzing the data from that high magnitude experiment, which had less of those river changes, those autogenic processes. I generated this movie of the delta, where the black line is the fluvial surface, the red circle is the shoreline, and the blue line is sea level. This movie helps us visualize how the fluvial surface in the experiment changes as sea level changes. You can see that the fluvial surface is moving in almost like waves, right? It has changing curvature. And if you look closely, you can see that the upstream is changing elevation at a different time than the downstream, just like that movie from the model earlier. So the next step in my analysis was to quantify how the elevation changed across the fluvial surface. I looked at 3 locations in the upstream and the downstream and in between. And remember, I took the radial average. So I averaged this whole fluvial surface into a profile that looks like this. So you can see our upstream in this black solid line, the downstream in this dotted line, and then the dashed line represents our middle location. And I tracked how these locations change in elevation through time. That's this plot. If you look at the y-axis, you'll notice that the changes oscillate around 0. And that's because I've removed the background sea level rise rate to clearly see the changes in elevation over time. Time here being the x-axis. The time is in hours because when we scale down the delta from field size to flume size, we can reduce the time needed to build a delta. In gray, I've shaded sea level rise, and as white is sea level fall. And you can see our 3 locations changing in elevation as sea level changes. One really clear example of this is here, where the dotted line, the downstream, is decreasing in elevation as sea level falls and increasing in elevation as sea level rises, which makes sense because this downstream location is closest to sea level. However, our upstream location is decreasing in elevation as sea level rises and increasing in elevation as sea level falls, which is completely the opposite. And you can see this kind of represented again here in orange. You've got this opposite reaction for the upstream and the reaction that matches sea level represented in this pink. And these opposite responses means that there's a shift in when the upstream is experiencing the changes in sea level to be about half a sea level cycle later. If we scale this back up to geologic terms, this is very long, about 50,000 years, because if you remember, sea level cycles every 100,000 years. So once I identified this time lag in the response, the next step was to quantify it across the whole fluvial surface. And here's that plot, where the x-axis is the distance from the river inlet, right, just like down here, and the y-axis is the time lag in hours over here. We do have a secondary y-axis that's the fraction of the sea level cycle period. So half of a sea level cycle would be represented by 0.5. And as you can see, our upstream location, this black solid line, does have roughly half a sea level cycle of lag, and the other locations, well, the time lag decreases as distance to the shoreline decreases. But the whole fluvial surface is responding to changes in sea level, just at different times. Once I quantified this lag, I turned to analyzing the changes in slope and curvature of the experiment, which caused the time lag. So just to set it up, here you can see 2 depictions of the fluvial surface in black. On the top is the high stand, and which is the very end of sea level rise, and on the bottom is the low stand, or the very end of sea level fall. In the high stand, you can see that the slope, which is this green line, is pretty mild, while in the low stand, it's pretty steep. You can also see that the curvatures are different. We have a convex shape here and a concave shape here. Changes in slope are easy to quantify for the experiment, but to look at changes in curvature, I had to come up with a metric called the departure from the linear, and it's symbolized by lowercase delta. So I'm going to say delta a lot, but here I'm referring to this, the value for curvature. To calculate this value, I subtract the actual curve in black from the green flat idealized curve and I divide by the length of a fluvial surface. So that equation is here. This means that a positive delta value here would have a convex shape, and a negative delta value right here would have this concave shape. So I calculated how the slope and curvature in the experiment changed with time. On the top here, you can see that the changes in average slope change through time. In this middle plot, you can see the changes in the departure from the linear, and the bottom is just sea level, and that's for reference. So in our top figure, you can see that as sea level is falling, which is the white shading, our slope is decreasing, becoming more negative or more steep. And as sea level is rising, it's becoming more positive and more mild. We get a similar story with the curvature. The fluvial surface has an increasing or more positive value as sea level is rising, and as soon as it transitions to falling, our value becomes more negative. So remember, a more negative value would be a shape more like this, and a more positive value would be a shape like this. And across the whole experiment, these changes in slope and curvature really follow those changes in sea level. So we know that the changes in sea level are causing the changes in the slope and concavity of the fluvial surface and causing a time lag in the upstream response to sea level. My next step was to understand how the slope and curvature were changing. Which brings us back to these plots from the beginning of the presentation. In these diagrams, again, we can see where the sediment is being eroded and deposited along the fluvial surface as sea level is falling and sea level is rising. So for the experiment, I calculate how much sediment is being deposited across the fluvial surface. It requires a few steps and a fancy math technique called normalization, but it allows us to calculate the amount of sediment being deposited and where for both sea level rise and sea level fall. These plots look like this, where the y-axis is the amount of deposition as the change in elevation, and the x-axis is the normalized profile. So 0 would be the river inlet where water's coming in, and 1 would be the shoreline where the sea level is touching the fluvial surface. So 0 would be here and 1 would be here. During sea level rise, we see that the most sediment was deposited in the upstream and at the shoreline. And during sea level fall, we've got most sediment being deposited in the middle of the profile. And these patterns of deposition match the shape that we would expect convex, right, during sea level rise and concave during sea level fall. So it's really the patterns of erosion and deposition that are driving the changes in curvature that cause the time lag in the upstream portion of the fluvial surface. The next step of my work was to see if these same dynamics from this past experiment were visible in the low magnitude experiment, which had more river channel changes that could potentially make it hard to see the sea level signal. So I started my analysis again by looking at the changes in elevation at these locations across the fluvial surface. Here, we're only looking at the upstream in that solid line and the downstream in the dotted line because these two locations capture the full extent of the changes. At first glance, it does look like the channel dynamics are obscuring the sea level signal because if you remember, the timing of the high magnitude elevation changes match the changes in sea level, which doesn't appear to be happening very often in this low magnitude scenario. Although there is this one point here where the downstream is increasing in elevation as sea level rises and the upstream is decreasing in elevation, which matches the previous experiment. But for the rest of the experiment, it's kind of hard to tell. So I looked at the overall trend in the data for each of these windows of sea level. And the windows are what I'm calling these gray and white shaded boxes of sea level rise and fall. And I calculated the trend in each of these windows by using another math trick called the average rate of change. And when we plot this average rate of change across the experiment, there is a trend in the data that matched what we saw in the high magnitude experiment. The upstream location is increasing in elevation during sea level fall, while the downstream is decreasing. As sea level rises, the downstream increases in elevation and the upstream is decreasing. These are the same opposite trends we saw in the first experiment, meaning that the upstream location is having roughly half a period of lag in when it responds to sea level. So, again, I looked at the changes in the slope and curvature of the fluvial surface across the experiment. Again, it's hard to see the trend here because of those river channel dynamics having a strong influence. But if we look at the trends through time, again, that average rate of change, those trends do seem to have a trend that matches the other experiment. As sea level is rising, the fluvial surface is more mild and has a more convex shape. And as sea level falls, the slope is more steep and the shape is concave. Again, these are the same slope and curvature changes we saw in the other experiment, where during sea level rise, the slope becomes more mild and the fluvial surface becomes more convex before transitioning to a steep slope and concave shape during sea level fall. So, to recap, under both experiments, two different kinds of sea level change, I identified a time lag in the upstream response to sea level, which is driven by changes in the slope and curvature of the fluvial surface, and those changes are caused by the patterns of erosion and deposition that occur as sea level changes. But why do we, and why should you, care about a time lag in the upstream response of a fluvial delta? So I explained how sequence stratigraphers have been trying to understand the rock record for a pretty long time and in a variety of ways. And my work adds another important piece in how we can understand, interpret, and reconstruct past sea level. But why is it important to reconstruct past sea level? I'm going to take this great quote from a conference on paleo sea level in 2016 directly from the experts. The geologic record serves as a valuable archive of ice sheet and sea level change in response to past climate variability. Therefore, the geologic record is an important resource for assessing the relationship between ice sheets, sea level, and climate change, and plays an important role in projecting future sea level rise. So, the more accurately that we can understand the geologic record, the better that we can predict the future. The work I did is just a small piece in making sure that we can accurately understand that past record, and is a small step forward in understanding how things can change in the future. I owe many thanks to many people, including my family, the MSU Coastal Dynamics Lab, my committee members, Jorge, Sandra, and Josh, and of course, the Tulane SEDSTRAT group for conducting the experiment and gathering the data I used in my analysis. Without all of you, this work would not have been possible. So, does anyone have any questions?